Hey there, astronomy students. This is Ms. Ruark. We are working on Vodcast 9.2. We're going to talk about the diameter of stars and the masses of the stars. Okay, so they had to come up with a way of organizing and putting all this data about stars into something that was going to be very useful for astronomers. Okay, so what did they do? Well, they came up with a system that's called, well, I don't know if you call it a system, but they came up with a diagram. It's a Hertzsprung-Russell diagram. We call it an HR diagram. Okay, and it just makes it a lot easier to be able to tell the luminosity and the temperature. Okay, so what do we know? We know that stars all have different temperatures. They all have different luminosities, and they all have different sizes. Okay, well, how do those all interrelate? Well, if to show some order in all of them, they decided to organize them into a diagram called the HR diagram. Okay, so going vertical on the HR diagram, the vertical axis is going to be your absolute magnitude or your luminosity. Okay, going horizontal is going to be your temperature or your spectral type, right? Temperature or spectral type. Okay, and that would be the HR diagram. Okay, here's a copy of an HR diagram. Okay, and if you see luminosity is here on the vertical axis. As you go up, the stars are more luminous. As you go down, they're less luminous. Okay, as you go from left to right on the temperature scale, you're going from very hot to very cool. Okay, so the very luminous stars are going to be found at the top of the diagram. The low luminosity stars are going to be found at the bottom. Your very cool stars are going to be found on the right, and your very hot stars will be found on the left. Okay, now here in the middle we have this called the main sequence. Okay, the main sequence is where 90% of your stars are going to be found. There you go. Most stars are found along the main sequence. Let's see, what else? I don't know. Oh, yes, the comparison with these. Okay, so like I said, 90% of your stars are going to spend most of their time and most of their active life in this main sequence here. Okay, by looking at this the HR diagram, you're going to be able to tell that temperature isn't the only thing that's going to determine the luminosity. Size also comes into play. Okay, but here we have two stars. One of them is a B1. I don't remember the names of them, but I think it's labeled later. Okay, so this would be a B star, and this is a B star. They're both the same classification, but they have a different subclass. Okay, this one's going to be roughly about 24,000 Kelvin, and this other one here is going to be roughly at about, I'm guessing here, 12,000 Kelvin. Okay, so if you'll see, these two stars right here, says same temperature. They're really not the same temperature. They have about the same luminosity though, right? Different temperatures, same luminosity. All right. Let's see, those stars that we just showed you here are some of these stars here. The brightest stars are all here in the same classification. I know there was a reason why I had that here, but I can't remember what it is now, so we're going to keep moving. Oh, okay. Well, open star cluster. Brightest stars are blue, and then the red ones are going to be the colder stars. Okay. The radii, or the size of the stars in the HR diagram. Okay, so these straight dashed lines here that are diagonal and slanted going down, along one of those lines, all of the stars located along that line would have the same radius. Okay, so here we have 1R with a little circle after it. Okay, all along this line, any star that's along this line is going to be about the same radius as our sun. Okay, any of them that are along this line here are going to be 100 times bigger than our sun, so the 100R. This one is 10R, so it's 10 times the size of our sun. These up here would be 10,000 times the size of our sun. Right? And then if we went down, Down here, we are 1/10 the size, 1/100th the size, 1,000th the size. Okay, so Rigel here and Betelgeuse here, both of those are stars that are in the Orion constellation. Okay, Rigel is going to be the brighter star. It's actually the hotter star too. Betelgeuse, however, is going to be bigger in size. You see, there's a relative size comparison here. It's not an accurate size comparison, because if it was, as I'll show you in just a minute, you wouldn't fit them all on here. Okay, but just to kind of go through these will give you an idea of the different classes or different types of stars we have. So all of these up here in the spot where they're 10,000 times the sun's radius and into 100 times the sun's radius, all of these up here, these would be our supergiants. Okay, our supergiants are 10 to 1,000 times larger than the sun. Rigel, which is right here, is more luminous than Vega. Where's Vega? Vega is down here, this little star right here. Okay, they are the same temperature, but Rigel's going to be bigger, so it's a supergiant. Okay, and then we have here in this little cluster, these would be our giants. Okay, the giants are right above the main sequence stars. They're going to be cool and luminous. They're about 10 to 100 times larger than the sun. Okay. Then we have, let's see. Oh yeah, that's what I was going to talk about. In these supergiants here, if we took Betelgeuse, which is in Orion, it's the red one in Orion, and replaced it with our sun, okay? Let's see how big this one is compared to our sun, which is like a little dot down here. It would swallow up Mercury, Venus, Earth, and Mars. Okay, so that just gives you a scale as to how big these supergiants are. Okay, and the largest supergiant stars can have a radius of up to 7 astronomical units. So if that was in place of our sun, it would be all the way out to Saturn. Wow. All right, so then here we have our red dwarfs, which are at the end of the main sequence stars. They're small, cool, and they have a low luminosity. They don't really radiate much heat, and you don't really pick them up too much when you're talking about absolute magnitude and apparent magnitude. And then here you have your white dwarfs. Your white dwarfs are lower left. These are going to be very hot and very small, very hot and very small, and they're roughly about the size of the Earth. Okay, so all these dots here, oh, there's the sun. All right, all these dots here give you, they're symbolic of the sizes, but if we were to use, like if we were to take these and show you the difference in the sizes, see how much bigger these supergiants and these giants are compared to the main sequence stars and even the white dwarfs and the red dwarfs. The dwarfs are so small, they really are dwarfs. Okay, all right, so let's see. Luminosity classes. Okay, so we need to remember that collisional broadening, which we learned about in the last chapter, increases spectral lines and is caused by dense gas that, and if the gas is dense, there's going to be a lot of collisions between those gas particles. Well, main sequence stars, these right here in the middle, these main sequence stars, these are all dense. They're small. They have a dense atmosphere, and the dense atmosphere will give a broad spectral line. Okay, more collisions. These giants up here, they're going to be larger, but they're less dense, and they're going to have narrower spectral lines, so more narrow spectral lines, or less broad. The supergiants are going to be even less dense, and they're going to have very narrow spectral lines. Okay, luminosity classes. Let's see if I have. Yeah, here we go. Okay, you can't really see it too well, but you have your luminosity classes. You have your class 1 is broken up into 1A and 1B. 1A is the bright supergiants. An example of that would be Rigel. Okay, and then you have your 1B, which would be your supergiants, and that would be an example of that would be Polaris. Then you have your 2, which would be your bright giants, and Adhera would be an example of that one. Then you have your class 3, which would be your giants. Your class 4, which would be the subgiants. And then your class 5 would be your main sequence stars. And of course, an example of that would be the sun. Okay, now if you see these lines that are drawn here, these yellow lines that are drawn here show you the class. So most of the 1A stars should be right along that line. It should be right on it, right above it, or right below that line. So if you see the sun is right along that line. All right, the subgiants, Altair is right in here. Okay, so they're all right along that line. Okay, so with this is telling us that we can look at a star spectrum and tell roughly about how big it is based on how wide or how narrow the spectral lines are. Okay. All right. So our sun is a G2 star, but if we were to show it with its luminosity class, what we would do is we would write it. We would write the luminosity class after the spectral type. So our sun would be considered a G25. Remember, Roman numerals. Okay, so G25, not G2V. G25. Okay. Polaris is another G2 star. It's a supergiant, though, so it would be G21b. Okay. Remember, Polaris is huge. Our sun, not so big. Okay, and then the spectral lines of the giants. So here we have a supergiant. Notice how the spectral lines are teeny tiny, very narrow, which means that they're going to be huge, less dense. Okay, if they're less dense, they have less collisions. If they have less collisions, that means that there's not a lot of gas, which, the gas isn't really close together, which means it's spread out. Tells you that it's a lot bigger. Okay, the giants, they're going to be a little bit smaller because the lines are getting bigger. Main sequence stars, they're a lot smaller because those lines are much thicker. Okay, okay, so absorption lines in spectra of giants and supergiants are narrower than they are in the main sequence. And then from the line widths, we can estimate the size and luminosity of a star. Okay. And I just thought that was just too funny. So I think that's all, and I'll see you in class.